Thank you. Thanks everyone for coming. I'm going to talk about tornadoes today, talk about some of the work our group has done on trying to understand the most devastating and long-lived tornadoes that exist. And we've been doing this work since the first PRAC 2, so I think we've used all three versions, the friendly user time, PRAC, and then some Illinois time as well. So I'll talk about where we've been, where we are, and where we hope to be going, talk about the scientific problem we're trying to solve, look at the computational aspect of this, and then show you some results on an actual successful simulation. We have created I believe one of the first simulations of a long-track EF5 tornado embedded within a supercell thunderstorm. We actually are using this from a real event that occurred in 2011. I'll talk a bit about I/O and visualization and some of the issues we've run up against, and then talk about where we hope to be going. So the strongest, longest-lived tornadoes, these are the ones like Joplin, Missouri, Tuscaloosa, Alabama, El Reno, that occurred earlier in 2013 that actually resulted in the loss of life of some storm chasers. The storm that, these are the big tornadoes, the ones that last a long time, the strongest winds. Because they're the rarest, they're difficult to they don't happen that often in the environment, and they also don't happen that much in the models, which actually makes some sense, but since we're trying to study them, we have to actually get one to happen. And there isn't a lot of research on this type of work in regards to numerical simulation because it does require a tremendous amount of computational resources. So we're trying to capture several of these events happening. We're simulating the entire thunderstorm. We want the tornado to form naturally, or actually just happen, and have it on the ground for a long time, and then have it decay, just like a real tornado would in a supercell. But we want to capture this for many storms. The first step, of course, is to get it happen once. We've gotten that. And then, of course, the overall arching goal of this is to be able to do better predictions so people don't get caught in these storms. We're using the CM1 cloud model developed by George Bryant at NCAR. It's a model that was written pretty much from the ground up to work well on massively parallel architectures. It uses, currently the orientation we're using is 16 MPI ranks per node with 2 OpenMP threads, so we're using all the cores, and so it's a hybrid model, and it scales quite well. We've got it up to 200,000 cores, and it scaled well. And the simulation I'm showing is a little bit smaller, but we hope to reproduce the simulation at higher resolution. Now, getting the storm, this is the biggest challenge. So I spent a lot of time working on I/O and Viz. I'll talk about that, but actually we had all our tools working, but then we didn't have our storm. We could certainly grow a storm in the computer, but we couldn't get it to form a tornado, or we couldn't get it to form a long-track EF5. So this was actually becoming quite troublesome towards the end of our PRAC, because if we don't reach our goal, our science goal, then we're just kind of playing with computers. So I experimented with a lot of different atmospheric environments. So essentially, we initialize the model with a horizontally homogeneous base state, and then we perturb the atmosphere and get a cloud to start growing. It's sort of like the computer is a laboratory, and the cloud grows, and then the supercell forms, and then hopefully the tornado forms. So we experimented with a lot of different things. Obviously, the resolution plays a huge factor in this. When you look at the size of a thunderstorm like this, the thunderstorm might be on the order of 50 kilometers in diameter in the horizontal, whereas the tornado might be, say, 50 to 100 meters. Okay, but you have to capture all those scales of motion, so it requires a lot of computation. We looked at surface treatments, friction, or free slip, microphysical parameterization. That's how the cloud precipitation is handled, as we saw in the first talk. There's a lot of parameterizations in cloud models, and we certainly have a lot of room to improve, but there's several options. Turbulence, how do we handle the subgrid flow? And then how do we initialize the cloud? There's different ways to initialize the cloud, and we're using a method that's just starting to be used more. And as with the real atmosphere, most of our storms did not produce the long-track EF5. So a lot of the work that was done early on was just getting I/O to be efficient. CM1 did not come out of the box with an I/O option that worked well in Blue Water, so I spent a lot of time learning more than I really wanted to know about HDF, and also different ways to parallelize, different ways to organize data. I settled on something that works pretty well. We now have a situation where I/O does not choke us when we're trying to save data every 2 model seconds. And when you see the movie I'm going to show you, because tornadoes, the air is moving pretty fast, we all know that. If you're going to actually study things, you need to save data very frequently, and that results in a lot of I/O. I also wanted to be able to visualize the data. When you start producing tens, hundreds of terabytes of data, you can be overwhelmed quickly. Since we're looking at something that's like an actual atmospheric phenomenon. It's three-dimensional. You want to be able to look at it, right? Well, there's a lot of grid points there. So I wrote a plugin with a little bit of help from Rob Cisneros at NCSA to actually interface with the data output format that I developed. And it's called a plugin, and it works pretty well. So what we ended up doing was we're actually doing serial HDF5 on each node, 1 core per node, collects data, it buffers it to memory. This was actually one of the things that made performance go way up. So CM1 model takes up about 3% of each node, okay? So that's a lot of data. There's a lot of memory available to do buffered I/O. So instead of saving data to disk at every write cycle, we just buffer it to memory, buffer it to memory, buffer it to memory. That's very fast. Eventually, for whatever reason, either we're running out of memory or we're trying to do checkpointing, we flush all that data to disk. And it's 1 file per node and with, like, say, maybe 50 to 100 time levels. And Blue Waters likes to write big chunks of data, many files, not too many files, but it really actually, you can saturate the pipeline, but you don't want to make too many files, and there's luster issues and such, but actually this works out pretty well. At the same time, when I wanted to see what's going on with the model, or just look at some two-dimensional surfaces, because meteorologists like to look at weather maps, right? They're two-dimensional surfaces. So at the same time I'm saving all these big fat 3D files, I'm also doing a very simple parallel HDF5 write to do 2D data. So basically taking an NX by NY two-dimensional thing and just doing a PHDF5, hoping that parallel HDF5 does the right thing and writes it to disk. This has been a little tricky to get to work efficiently, but these files come out every 30 seconds or much less frequently than the 3D data, so we do lose a little bit, and there's some issues with that are still haven't worked out, but we can look at that data quickly. So we were at the end of our first PRAC without our supercell, and then suddenly I'm watching the data come in one day during a run, and I see the pressures drop about 100 millibars. I thought, okay, the model's probably blowing up, but no, actually a tornado was forming. And the tornado was on the ground, and we actually got the storm we were looking for. Then we ran out of time, so we quickly wrote an Illinois proposal. Robert Wilhelmson being the PRAC and a former U of I faculty member, we could do that, we got some time. Then I found out I made a problem there's a problem with the environment in which I simulated the storm. For about a month I was just like suicidal, not really. I reran the simulation with the fixed environment and managed to get the tornado back, so that was good. So what's this about? This is about a specific event. So this is not the El Reno tornado that happened earlier in 2013. This is another EF5 tornado. So if you want to see EF5 tornadoes, go to El Reno, Oklahoma. It's just outside Oklahoma City. Maybe you'll never have it again. Anyway, this storm that we're basically trying to simulate had a 65-mile path, and it was EF5. That's the largest, that's the strongest scale for the tornado that we have. And our simulation actually used the conditions that were surrounding that supercell while it was happening. So basically in meteorology, we assimilate data into our weather models based on observations, also on previous model runs. We sort of blend them together. We basically took a column of air that was feeding the storm that actually happened and used that as the initial conditions and ran the model. And this was a successful strategy. The simulated tornado actually is on the ground for almost the same length as the one that happened. In fact, it's still on the ground when I stopped the model running, but it was weakening. Winds exceeding 300 miles per hour. That's insane, but it's not unprecedented. There have been Doppler radar observations that have shown winds that have been up to 300 miles an hour. So we don't think this is off the charts. However, this is a friction-free run, and we tried a lot of different things, and we were sort of scaling back and simplifying. And one of the things we did was turn friction off at one point, and this actually seemed to lead to a good result. Now, we are doing some analysis with the run with friction on it. We still get an EF5 tornado, but this is work in progress. So we got the simulation to work. Then this was a simulation where we only save data every 30 seconds or so. We use this strategy because we don't want to write tons of data if we don't have to. So we go on fishing expeditions, we get a storm before, and then we go back and we run it from checkpoint files. And this is actually a practical approach for us. So I use the Visit volume rendering capabilities of the Visit visualization tool that runs on Blue Waters. Visit's really cool. You can sit at your workstation at home. It connects to the Blue Waters machine. It spawns jobs into the queue, many processors, and spits the data back to the screen. So I'll show you some pretty pictures. This is a view of, say, if you're looking at a supercell from, say, 100 kilometers away, looking towards the north. The features you see. If you're not a meteorologist, this is just a cloud field, so you see the anvil, the overshooting top, the mesocyclone, And right over here, this is a little tail cloud, wall cloud, and there's a tornado there. But this gives you an idea of the scale of the storm. We have to simulate this entire storm at high resolution, or actually I should probably qualify that. We do use a stretched horizontal grid, so out here the resolution is a little less, out here it's less, but we have to, half of the model domain is run at very high resolution. Continuing to zoom in, you can see now there's an EF5 tornado, but again, we have to capture this whole storm at this resolution. So, and this looks kind of like, if you kind of fuzz your eyes out a little bit, you might almost think it's a real cloud. And this is the kind of thing that hasn't really been done to a very large extent in computational meteorology. We're now to the point where we can simulate a supercell thunderstorm, have it produce a tornado, have it produce features like a wall cloud, a tail cloud, a condensation funnel, without doing anything, any tricks. So here's some different stages in the storm focusing on the region of interest. So this is a descending condensation funnel. This is this sort of purplish gray field is rain, and then the gray field is cloud. What I basically did was I created an expression in Visit that captured both of these fields, because you can't volume render two different fields at the same time for technical reasons. You probably can, but you have to instruct how to do it. So we see over time, this is the rear flank of the storm. This blue field here is the surface buoyancy, so you're seeing primarily cold air from evaporation and other thermodynamic processes that occur in the storm. So out here in the white is the interface. This is the interface between the environment and the storm-generated air. We see some very realistic looking features, nice wall cloud. This feature here where you see the rain is sort of a very thin rain curtain surrounding the tornado. This has been observed as well. Very nice looking wall cloud. This gives you a sense of scale here. We're running at 30-meter grid spacing, 30-meter resolution. So, you know, when you look at the size of a tornado, you've got about, 5 to 10 grid points across the tornado itself. So technically, you can finally say you're actually resolving the tornado. Maybe not really well, but it's typically in meteorology, when you get something that looks like a tornado, you call it a tornado-like vortex because it isn't resolved well enough. We see features that are positively buoyant RFD surges, roof flank downdraft surges. So not all the downdrafts that occur over here are cold from evaporation. There seems to be some other things going on due to maybe compressing the environment. Some of this air is warm. This is something that's also been observed when people go out and chase storms, etc. And so on and so forth. This storm just keeps going. We see some features that are subtornadic. So this little thing right here is an actual horizontal vortex that is spinning very rapidly. There's a pressure drop in there, and you're actually seeing a condensation funnel, horizontal condensation funnel, essentially. This has also been observed. And here's what, I'm using some of the terminology that meteorologists use sometimes. This is like a wedge tornado. Now you have a rain-wrapped wedge tornado, so this is the kind of really dangerous situation that some people find themselves in when they can't see the tornado. So I did some fun things with Visit. So here's our storm in motion. So we're actually capturing the storm tornado forming. So keep your eye focused right on here. This is rain, this is the mesocyclone, this is a tail cloud, and this is a wall cloud form right here. And or maybe we could hit the lights. I don't know if we can do that or not, but it might look a little better. But if not, it's okay. And then we see the tornado forming. Now, again, this is every 2 seconds. So we're saving data very frequently. There's a lot of things that happen very quickly. And without being able to save data this frequently, this is something that Blue Waters enabled us to do, you really start to capture features. You can also communicate better with actual storm chasers who don't do numerical modeling by showing them pictures that look like what they see when they're in the field. So I'm very interested. I've always been very much on the interface between computing and weather. I love computers. I love severe storms. But it's very important to me to create something to visualize. The visualization part is almost as much fun to me as just making the scientific discoveries. So as you can see, I could probably talk forever. Time is going by on this side. This tornado continues to change. It's going, 300-mile-an-hour winds near the ground. And you know what? Don't bring the lights up yet. I'm going to show you the vorticity field as well. So this is, what you'd see with your eyes pretty much. But now I'd like to show you something else. So now we're going to look at vorticity. So vorticity is a measure of the spin of the air. So this is the 3-dimensional vorticity field colored by the vertical vorticity magnitude. So in other words, this red guy is rotating counterclockwise. This blue guy here is rotating clockwise. This is this part of the storm you want to focus on. This is where the tornado is forming. Now at this point, We don't have a tornado yet. This is something that I found that's very interesting. So before you see a condensation funnel descend to the ground, you're actually seeing this well-defined vortex formed already. So you might, if you were chasing this storm, you might start to see the winds, kicking up some debris. Exactly when the tornado forms is sort of a subjective thing. We noticed that a whole lot of vorticity is being sort of, these little guys here, these are subtornadic little vortices, are sort of being ingested into the main flow. You start to see what's called vortex breakdown occurring in the tornado. This is something that's been seen in simulations of tornadoes themselves, and where you just simulate the tornado, not the entire storm. You can see it's very chaotic. There's a lot going on. You see these surges in the rear flank gust front, these warm air. You see a lot of little vortices. You notice there's constructive interference, essentially, when you sort of the vorticity is absorbed into this tornado, and sometimes destructive interference, I call it. For instance, keep your eye right on this area here. You sort of see this sort of lazy anticyclonic vortex that starts to grow. And watch how it interacts with this guy right here. Kind of goes around it gets tossed, it gets turned into the horizontal, and that's where you start to see these rolls occurring around the actual tornado. There's enough pressure drop inside that roll where you start to actually see a cloud forming, just like you see in the cloud here. So sometimes the tornado is sort of laminar, it doesn't seem to be very chaotic, then you see these blasting things going on in the rear flank. I mean, really, it's very interesting. There's a lot going on here. There's a lot to analyze. But again, this wouldn't have been possible to do. Well, it might have been possible to do on, say, an Exceed storm resource, but the fact that we were able to have a quick turnaround time and have basically an end-to-end solution from development to running the model to developing the visualization, running the visualization, and then putting this all together. This is something that Blue Waters has just really, really been good to us for that kind of application. So these are some cool things. So let me finish her off here. So issues with ray tracing, this is something I can probably talk to the Visit guys about the most. It was not easy to get that high fidelity out of Visit by just basically throwing a lot of cores at it. There's an issue with Visit. If you start to increase the numbers of samples per ray for doing ray casting, the memory utilization just goes through the roof and you start running out of memory. And throwing more cores at it actually makes the problem worse, not better. So what I ended up doing was I made how many frames did I do? I did about 3,600 frames, what you just saw, 1920 by 1080, that's 1080p resolution, and I ended up basically doing it in serial, but it's parallelizing in time. So what I ended up doing to get that many frames to be created was I essentially just made a whole bunch of Visit jobs by using the Python interface. I made a Python script that spit out a bunch of Python scripts that were then initiated with a shell script. And the Visit people will probably cringe when they see me doing this, because then I ended up with issues like, well, when you run a Visit job like this, it stays attached to the terminal from whence you started the job. So I ended up basically running out of too many files open because they had this. It was really kind of a pain. But I got it to work. This is where virtual terminals are nice. VNCs are nice. You just close it and it's off to the races. So this is not the best way to do it, but it worked. And Visit and the whole Blue Waters environment enabled this. It wouldn't have been possible on simpler machines. You can look at the movies. I do have a little site there. So okay, where are we going? This is an exciting simulation. However, there's no friction at the surface. This is something that needs to be dealt with, and we're dealing with this because the real ground is there, and by turning friction on, it does have a very strong influence on the simulation. The reason why we turned friction off, and I didn't want to turn it on too quickly, was because we ended up running with basically an isotropic mesh near the ground. So the first grid point is about 15 meters above the ground. Now, because the inflow into the supercell is usually very, very shallow, if you turn friction on with too coarse of a grid, you end up affecting the dynamics in a very negative way. So our hope is that we can basically increase the resolution, increase the grid resolution near the ground, and do friction correctly. But even with the grid that we have, I've managed to turn friction on, basically having the storm move over a region of gently increasing surface drag, and we still get an EF5 tornado. And it actually looks a little more physically realistic than the one I just showed you. So we've had some success running this. We hope to basically be able to run from restarts. These simulations are extremely sensitive to the initial conditions. So when I went back to redo a simulation once, just because I had a problem with the environment, it didn't give me the same storm, even though the change I made was so small. And even going back and just changing the time step can make the simulation go from a tornado to no tornado. So I'm running from restart files once the storm has been established, and I hope to basically write code that allows me to interpolate the restart files or the checkpoint files onto a more fine mesh, and then get a tornado to form, but under higher resolution conditions. So in fluid dynamics, you run into computational stability issues when you increase the resolution, because you also have to decrease the time step. So if we double the resolution, we need 16 times more service units, and that's on the low side of things. So the run I showed you was 10,000 cores, or 20,000 cores if you count 32 cores per node. And we've run simulations that are about 10 times greater than that. So in order to do real science here, we're going to need to run at higher resolution and do several simulations. So I think this is arguably still very much a Blue Waters problem. And again, I should reiterate that really nobody's done this before, at least it has published the data. So this is a pretty exciting thing for us. So I'm looking forward to moving beyond technical issues and doing some science as long as I have time on Blue Waters. We've done a breakthrough simulation. The Blue Waters environment has been very good to us. I'm very satisfied with the machine. Once I discovered IBM wasn't going to make the machine, I was all bummed out. And not that I have anything against Cray, but then basically I've been very satisfied. I have to say it's been a good environment. Even with Lustre, which I've never liked that much, it's actually Lustre performance is pretty good. They did the right thing when they the way they spread it out. And I think our existing tools are pretty solid, and I think now we're ready to do some real fun stuff. So that's all I've got. Thank you.